Alright, section 2.6 deals with continuity. So continuity is a key concept. It's used a lot in higher math to support a lot of theorems. You require continuity in order for the theorem to work. So it's important that we understand what continuity is and when is something not continuous or discontinuous, and what are the types of discontinuities to be on the lookout for. So here I've drawn a couple examples in red of continuous functions. Okay, so just, there's no break in the graph. You can draw a continuous line without picking up your pencil. Those are continuous functions. On the right hand side here in blue, I've drawn some discontinuous functions, and I've drawn 3 different types of discontinuities. So this first one here is something we'd call an infinite discontinuity. Let's just abbreviate that. Down here we have something called a jump discontinuity, and the last one here, we would call that a removable discontinuity. Okay, it's just discontinuous at one point. Okay, so here's the formal definition of continuity at a point. A function f is continuous at a if the limit as x goes to a of f of x is equal to f of a. And then there's a continuity checklist. F of a needs to be defined. The limit as x approaches a of f of x exists, and the limit as x approaches a of f of x actually equals f of a. Alright, so let's do an example and try to examine some cases where discontinuities occur. So in this first example here, we're asked to determine whether the following functions are continuous at a given point. So for part A, we give it, well, I guess for both parts, the point is x equal to 1. What's happening there? So for part A, if I try to evaluate the function at 1, I end up with a non-real number. So here f of 1 does not exist. It fails one of the key criteria of what we need for continuity. So this function might be continuous for a certain interval of x, okay, namely when x is greater than or equal to 2, but it's discontinuous at x equal to 1. Okay, so let's look at part B here. Here we have a piecewise function. Notice that the piecewise function equals x squared minus 1 over x minus 1 when x is not equal to 1, and it equals 3 when x equals 1. So I want to examine what's going on at 1, which is kind of our breakpoint. So the first thing I'm going to do is I'm going to simplify this rational expression. So if I simplify, I'm going to get the following. Okay, so here you can see that I factor the numerator into x minus 1 times x plus 1. We can then cancel the x minus 1 over x minus 1, okay, because x minus 1 over x minus 1 is equal to 1. And so the whole piecewise function simplifies down to what I have written lastly here. Okay, it's equal to x plus 1 when x is not equal to 1, and 3 when x is equal to 1. Graphically, what does that look like? Well, it's the line x plus 1 with a hole at 1. So here we go, that's the first piece, and then we have the second piece of the piecewise function telling us that at 1 we're assigning the function value of 3. So this is an example of a removable discontinuity. Basically, the limit as x approaches 1 of our function f of x is equal to 2. Okay, the limit kind of goes along with this top piece. If we approach from either the left or the right, it seems like we're approaching 2, but there's actually an undefined point there because of the original denominator x minus 1. Okay, that point is not, you can't have that point, there's a hole. And because of our piecewise definition, f of 1 is equal to 3. So we see that the limit at 1 does not equal the function value at 1. So therefore, this is discontinuous. Okay. Next example. So now that we've examined what continuity means and what it doesn't mean, now we're going to use it to evaluate a limit. So, the square root function is considered a continuous function on its domain. So that means we have some additional limit flexibility. We're actually allowed to pass a limit into a composite function as long as it's reasonably continuous. So I'm going to go ahead and rewrite this statement with the limit statement passed inside of the integrand. Okay, so passing the limit statement in, we get the square root of the limit as x goes to 4 of this rational function. So then what I did was I took that rational function and I factored the numerator. And now we can see that x minus 4 over x minus 4 simplifies down to 1. So we're left with the square root of this limit. And it's just going to be x times x plus 2. So we can use direct substitution to see that after simplifying, we get the limit 2 root 6. Okay, and I'll leave it to you to fill in, a couple of the steps in between this guy and this guy. Okay, next example. Okay, so this is very similar to the last example, but with a different type of function. Because tangent is continuous on its domain, we are allowed to do this. So we are allowed to pass the limit statement in. So we would have the tangent of the limit as t goes to 4 of t minus 4 over root t minus 2. Okay, now this looks a little tricky, but we can actually factor the numerator into root t minus 2 and root t plus 2. So let me write that out. Okay, now we can see that we've got root t minus 2 over root t minus 2, simplifies to 1, and we get the tangent of the limit as t goes to 4 of root t plus 2. We can now solve this with direct substitution, so the root of 4 is 2, so we end with the tangent of 4 as our limit. Alright, so last concept here is the intermediate value theorem. So the main thing about the intermediate value theorem is that it requires a continuous function on an interval, on a closed interval. So if you have a continuous function on a closed interval, and you have, say, an f of a and an f of b, the only way to connect these and retain continuity is if you pass through every single value between f of a and f of b. So all the values that are intermediate between f of a and f of b. So this theorem is used a lot. One application is in numerical analysis. It's called the bisection method. Okay, it's maybe one of the first higher math numerical analysis methods that you might learn. In this class, we're mostly going to be investigating finding roots of functions. So my next video is going to be an example of how we are going to utilize the intermediate value theorem in this class.